Okay, this is Mr. Hunt here. I'm talking about radians, okay, radian angle measure. Let's refocus that. You're going to need to go to this website at the top, mathisfun.com. It is, yeah, /geometry/radians. So the first paragraph there will talk about, I'll kind of sum it up. When you measure something, a length, inches, centimeters, feet, whatever it is, those are different units of measurement, and so far you've probably only ever talked about angles measured in degrees. But there's one other one that you'll primarily do throughout high school that's helpful, and the unit will be radians. And radians are based on radius, okay, or the radii of circles. And what it's really based on is a fact that all circles are similar. We're going to do an example of that below to kind of show why all circles are similar. We've actually done it at the start of our circles unit with transformations. We showed that. And I want to say here that since all circles are similar, the ratios of the corresponding parts will be constant. Okay, so let's see that in the next exercise. So I'm going to do this exercise, and then we're going to refer back to that Math is Fun website in a minute. So in this one below, I just want to show you why something like arc length or something, because all circles are similar, we can do common ratios between different circles, but the ratio should still be the same of something like arc length. All right, so that's what we're going to do. So in this one, two circles are shown. They both have the same central angle, 60. They have different radii, though. And we're going to find what they call S, the arc length. So we're going to do the arc length formula. So this is a good review of that. It's the arc over 360, arc or central angle, over 360 times 2 pi times 2 pi r. So this first one, the radius is 5, and that central angle arc measure is 60. Okay, and then the next one, same central angle measure slash arc, 2 pi, but the radius is 8. Okay, take a second. Again, maybe pause the video right here just so you can work it out. And what you're going to get, if we came back here, this one is 1.67 pi, so about 1 2/3. Technically it is 1 2/3 pi. And then the one on the right, 2.67 pi. All right, so 2 2/3 pi. Okay, and that's great. Certainly the one on the right is going to have a bigger arc length, it's a bigger circle. But now what we're going to do is compare that with the ratio, do a ratio comparing that with the radius. So the first one, the arc length, 1.67 pi over the radius, which was 5. And the one on the right, we'll do the same thing, 2.67 pi over the radius here, which was 8. Again, put these in your calculator. So do 1.67 pi, divide by 5. Then I want you to do, oh, actually, I left mine without pi. You'll get the same, different numbers, but the same result. Over here, I did 2.67 divided by 8. Here I did 1.67 divided by 5. And here's what you get. Again, try these out in your calculator. You get 0.3 repeating here, 0.3 repeating pi. Here, guess what? 1/3 or 0.3 repeating pi. Again, if you enter with the pi, you get the same number, but it would be whatever 1/3 times pi is. Okay, so what we found is that even the circles were different. They're all circles are similar. So when we actually do something proportional, those ratios, you get the same thing. So this leads us to an important point. Okay, and that point is that the only thing that, because the circles have the same central angle, the radius even though it was different length, it didn't affect the overall ratio there. Below, I wanted to show you, this gives rise, and I'm going to show this in a minute, to a different, on the next page we'll talk about the arc length a little more in detail, but the radian rotation formula below. So a radian rotation of arc length, which we'll say the arc length is s. I'm looking over here. The angle in the middle, remember theta is the angle, is s over r. Okay, so it's the arc length divided by the radius, which is what we did up here with these. I say, well, it appears that the radian measure about a circle depends on the size, but it doesn't. It doesn't, because all circles are similar. Therefore, the ratio only relies on the rotation itself. The radian rotation truly measures the number of radii, this is important, that can be laid out along any curved length in a given rotation. So that's really, this is really, I put in bold at the bottom, what a radian is. How many radii you lay out on the curve of an arc. To show you what that means, I want you to go to the website. So go to mathisfun.com. Go to mathisfun.com. I'm going to get it set up here too. Okay, and so make sure you go to that website. Pause the video now if you need to go to that website. It's very simple but really good. I want us to look at a couple of things on there. The first one is that first drawing where it has, it just has, I could put it on a coordinate grid, I guess I didn't have to. But it has, this is the length r. And 1 radian is the angle measure that goes, if we were to put this radius, if we were to put this radius and wrap it along this arc of the circle, pretend that goes around, if we were to wrap that around right there, that's what they say the length is. Okay, that length of the radius r. We put it that length here, and whatever that angle goes to, that's what 1 radian is. So from there to there. Scroll down on that. They say it's about 57.2958 degrees. The radian is a pure measure based on the radius of the circle. So I want you to hit that next button. I'm doing it over here on my other computer. And it's just a cool little illustration of that. I mean, I really, really like that. Where they take this and they just bring it down here and they wrap it around. Okay, so hit the play button on that. They wrap it around of that circle. There's a circle that's kind of faded. And they take this radius length and they wrap it around the circle. It's very cool, and it illustrates, right, that's 1 radian. All right, we wrap that around. And then I just want you to go down, you're going to hit where it says radians and degrees. Let us see why 1 radian is equal to 57.29. So that's it. And again, it doesn't, what we did before, it doesn't depend on the size of the circle. I could have had a much bigger circle, take this radius, wrap it, go about right there. Guess what? It's still the 57.2958 degrees. All right, so it doesn't matter on the size of the circle. That's 1 radian. Now here's the really cool thing. I want you to hit, so radians and degrees, and it says, let us see why 1 radian is equal to 57.2958 ... degrees. Hit that video below. It's really, really cool. It has a similar circle, but then they say, all right, they take 1 radian, they have this, then they put another radian, and it goes there. Then they take a 3rd radian, and it goes about right there. That's the center, this is the diameter. And then what's left over? Well, guess what? It's 0.14159 ... radians left over right there. So you'll have 123.14159. And guess what? That's pi radians. So pi radians, again, this is a degree, is 180 degrees, halfway around. Isn't that cool? Another reason, this is like when you go on to, especially pre-calculus, you'll use this fact a lot, just so much that halfway around the circle is pi amount of radians. So what that means is there's, again, 3 radii, 1, 2, 3, 0.1415 left over, 3.14 pi radians. Okay, you can get off that website, the Math is Fun one, and flip the page over to page 11. And what we're going to do is talk about a few things. Here's one of the most important reasons we just discussed a little bit. This is really kind of what the air test wants you to know a little bit. I want you to know how to convert these. So we just mentioned 180 degrees is pi radians. And so hopefully that leads you to conclude if halfway around is pi, we go a full length around, we'd be at 2 pi. So 360 degrees is 2 pi radians. And the air, OST, wants you to know how to convert that. So look at this little table below. To go from degrees to radians, and this is not on the formula sheet, but they do want you to know this. They'd probably have one question on there about this. To go from degrees to radians, multiply by pi over 180. It's just a conversion. The conversion is either one of these from above. That pi radians is equivalent to 180 degrees, or 2 pi radians, you can write RAD for radians, is equivalent to 360 degrees. So it's up to you which one you like. I mean, you can see that pi over 180 is just a simplified form. Okay, and the conversion to go backwards from radians to degrees is multiplied by the reverse, 180 over pi. All right, I'm going to do a couple of those and then show you why one of the formulas works at the end to wrap up. So I say here, wow, we kind of already did this. One complete rotation is the same as how many radians? Well, if you didn't know, we said it above, but 360 is one complete rotation, and you do times pi over 180. This is the conversion. So the degrees cancels out. Again, the radian. 360 over 180 is 2, and then you keep the pi. So 2 pi radians. We kind of mentioned it above. 1 radian is the same as how many degrees? So 1 radian, these are all just conversions. Radians to degrees, 180 over pi. Oh, that's a bad pi there. 180 over pi. Yeah. And so when you do that, 1 times 180, it's just going to be 180 over pi. And when you put that in your calculator, I want you to try that. Try that one for a minute, and we'll pause the video. Should put approximately equal to. It's that 57.296 that we saw earlier. 2958. It's 1 radian. Okay, we talked about earlier. About 57 degrees. All right, so let's see another one that you might see. Convert 30 degrees to radian measure. Well, 30 degrees, it's degrees to radians times pi over 180. So the degrees cancel out. I didn't say it here, but I should have mentioned leave this one in terms of pi. So you leave the pi, and we do 30 divided by 180, which is 1/6. So you can write your answer like that as 1/6 pi, or you can just move 1 times pi as pi and just move it up as pi over 6. All right, and the last one is 30 radians to degrees. So kind of reverse of C. 30 radians, so it's 180 over pi this time. I should really write, radians and degrees, so these cancel. So 30 times, multiplying across 30 times 180 is 5,400. I really just did 3 times 18 is 54 and tacked on 2 zeros. 1 times pi is pi. And put that in your calculator. Again, take a second, put it in. It's about 1,718.87 degrees. And I mean, we knew 1 radian was about 57 degrees. So multiplying that by 30, yeah, it's going to be a fairly large number. What does this represent, by the way? Guys, it represents 360 is one rotation around. 720 is another. It just represents going around again and again until you get up to 1700. and 18. No problem. So that's what it represents, going around multiple times. All right, that's a key thing that I want you guys to know is this: degrees to radians, radians to degrees. Okay, and the last thing I'm going to show you is we did this a little bit with talking first about arc length and area of a sector, and we showed why the formulas work. And I'm just going to show you really quick how the formulas can change. Now you only have to know the formulas for in degree terms. But if we do the formulas in terms of radians, the formulas are actually a little simpler. Okay, I don't think you have to know this for finding it in terms of radians. I'm going to ask you in degrees. Okay, but this is kind of fun. So earlier on, we said because all circles are similar, and let me draw out, I'm looking at here, like a radius, and theta is really just, we take one sector in that circle. So because all circles are similar, we can do a proportion relating in this case, I'll start with arc length, relating the arc length to the angle. So we did this before, but now I'm going to do it in radians. So I'm going to write here the perimeter of the circle over the whole angle of the circle. So top is perimeter, bottom is going to be angle. All right, so I'll just put P, and this is angle. Well, the whole angle of the circle, if I'm in radians, is 2 pi. When it was, we wrote 360 back on like page 3 when we were doing this. All right, so that's the perimeter of the circle over the total perimeter, total angle, 2 pi. And we're going to pair that with the parts. So the part that I want for the circle, we just call it S, is arc length. There's that little part there. So I'm going to call it S. So you just write arc length if you want, compared to theta. Okay, the part that we want. Now, if you remember, we can change this. Perimeter of the circle is circumference. That's 2 pi r. And look what happens. The 2 and the pi's cancel. I got S over theta, and all I'm going to do is multiply both sides by theta. Theta times r is arc length. This is it in radians. In degrees, if you remember, it was the measure of the arc over 360 times 2 pi r, which is the formula we're probably going to use more often. But look how much simpler radians made it. Okay, and that was because we changed it to 2 pi r. For the circumference, it cancels. It's just much easier. All right, let me show you really quick with area of a sector how, it's pretty similar in how it changes. So it's the same thing because they're proportional. I'm going to do area, though, of the sector. I'm sorry, area of the circle, the total, compared with the entire angle, which is, again, 2 pi for a full circle in radians. And then over here, we're going to do area of the sector, compared with the part we want, which is just theta. So back over here, it's like finding this entire area compared with that angle. So total area, total angle, part of the area, part of the angle. So that's a true proportion. And then we change the area of a circle to pi r squared. Writing area of the sector over theta. The pi's cancel, so not as much cancels here. We multiply both sides by theta, and we get the area of the sector is pi r squared over, theta r squared over 2. So again, a simpler formula than the measure of the arc over 360 times pi r squared. It's just fun to know that there's these simpler formulas that result using radians. Again, we'll probably mainly be doing these formulas in degrees, though. All right, thanks for watching. This has been Radian Measure with Mr. Hunt.